Hello, everybody, getting ready for finals. My name is Mr. Folly, and I am going to do this review guide with you guys so you can see it and have an answer. Now, before we do that, I think it's important that you look and see at the Chem 101 final exam provided information. It's very helpful to familiarize yourself with what's here. Periodic table, yeah, no kidding. Oxidation state. So, how you can tell oxidation numbers of these things. So instead of oxidation state, everybody calls them oxidation numbers. I know I do. So the oxidation number of an element in its free and combined state is zero, the zero rule. The oxidation number of monatomic one atom is the same as the charge on the ion. Rule 2 says use the periodic table. Rule 3, the sum of all oxidation numbers in a neutral compound is zero. The sum of a polyatomic ion is equal to the charge of the ion. So ions add up. My pen's so fat. Oxidation number is an alkali metal is +1. That's still the periodic table number. Oxidation number in column 2 is +2. Oxidation number of fluorine. So this is all rule 2. So these are all just periodic table. Okay. So I do these a little bit differently. I say oxygen is always -2. Hydrogen is always +1. And trust the outside more. But we got to get to that problem. Let's look at what else is here. Avogadro's number, that's good. Torr, millimeters of mercury, so these are pressure conversions. This is R, they only give us one R. So because they only give us one R, that means we're going to have to convert into that, or they'll probably always use atmospheres. PV equals nRT, density, another PV equals nRT, good, the other format for it. And then another way of showing the combined gas law, STP, remember this one, this is so forgettable. Converting Kelvin to Celsius, dilutions, and I use it for titrations. And then some pH things. Kw is H3O positive times OH negative. There's pH, POH, Q equals mc delta T, and those are all defined. Oh, the energy for electron jumping. Electron jumping. So those equations are here. E equals hc over lambda. That's good to know because I use a slightly different form, usually with two of them in there. A equals A naught. Ooh, man, oh man, oh man, oh man. These look like the half-life equations in a way that I'm not used to seeing them. 1 joule is a kilogram meter per second squared. I doubt we'll need that. You do need to know milliliters a centimeter cubed. Oh no, you have to remember all of your shapes. Oh wait, you don't. So the reason why you don't, you can count the number of bonding groups. I wish it didn't just say that. I wish it just said bonds, right? And non-bonding groups. I wish it didn't say that. I wish it said pairs, right? Because that's what they are. And then total number of electron cloud groups. And then all those are in there. EMF series, increasing activity. So this is my activity series. And then I have electronegativity values. This is electronegativity, so I can find polarity of bonds. And that's it. All right, so we may have to jump to that. Let's do some problems. What is the mass of a, so the first thing I'm going to do is give myself some extra room on all these. So page 1, sorry, dude, I can give myself some more. You might be able to write smaller than me, but. Okay, that'll get me through some. What is the mass of a 245 centimeter cube gram sample? Okay, so an equation they didn't give us was density. Density equals mass over volume. I swear my pen just got fatter again. It did. So weird. So when I see this, what I need to look for first is to make sure that my units jive. So centimeters cubed, that's good. So I've got 8.94 equals the mass times, this is the volume. So you need to know that grams per centimeter cubed, it's a mass over volume unit, is going to be your density. And then centimeters cubed is the density. Let's start the calculator. 8.94 times 245 is 2190.3. So M equals 2190 grams. And I know it's grams because this is grams. I just want to point out this has 3 sig figs. This has 3 sig figs. My answer will have 3. Calculate the energy of the visible light with a wavelength of 475. Looking at my equation sheet again, E equals hc over lambda. That's kind of nice. So looking for the energy again, E equals h. Oh, I forgot what h is. I didn't. It's 6.626 E negative 34. But I just want you to see that it's here. Speed of light's here too. So 6.626 E negative 34 times 3E8. And I just want to point out, if you look at the units, and I just want you to know this, nanometers are a trap unit. The prefix nano means e to the negative 9. Okay? So that means this is going to be over the wavelength, which is 475 e to the negative 9. You probably don't care why, but the speed of light is meters per second, and if it's meters per second, then my length has to be in meters. These units, again, have to jive. Okay. So calculators assemble. 6.626 e negative 34 times 3e8 divided by 475 e negative 9. So notice I didn't move the decimal. I just threw an e negative 9 on there. And my energy is 4.18 e negative 19 joules. Remember, energy needs to be in joules, and wavelength must be in meters to do calculations. Okay. How many moles are 125 grams of butane? 125 grams of C4H10. I hate you grams of C4H10. I'll put that unit on the bottom. And I'm going to go into moles of C4H10. 1 mole. Little g stands for grams, and little g stands for go to the periodic table. So I have 4 carbons, which are 12.01 each. And I have 10 hydrogens, which are 1.01 each. 4 times 12.01, enter, plus quantity 1.01 times 10, plus quantity is 58.14. Remember, multiply times things on top, divide by things on the bottom. 125 times 1, yeah, right, divided by 58.14. And I have 2.15. Notice how this unit cancels, diagonal things cancel. Moles, C4H10. All right. Half-life of zinc is 2.4 minutes. If I had 100 grams at the beginning, how many grams would be left after 7.2 minutes have elapsed? Okay, so the way I do this is I do this a time and amount table. My original time is 0, and the amount I have is 100. And every time I go down, my amount is going to be divided by 2, and every time I go down, I'm going to add a half-life. So the half-life is 2.4 minutes, so 2.4 will get me to 50. So it says how much will be left after 7.2 minutes has elapsed. So 2.4 plus 2.4 is 4.8, and then 7.2. 50, 25, 12.5. The answer is 12.5 grams. Okay. The equation below shows the synthesis of lithium hydroxide. Hey, that's right, making lithium hydroxide. How many grams of product can be made by a reaction with 20 grams of lithium hydroxide in excess? So if it says excess water, that means I don't need to worry about it. Okay. How much the excess reactant will be left over? Whoa. How many grams of product can be made by the reaction of 20 grams of lithium oxide? Okay, so this is missing something here. How many grams of product can be made? So I'm going to start with 20 grams of lithium oxide, and I'm going to show you what it probably meant to do. If excess water, that means I don't have to do a limiting reactant problem, so I'm not going to. So it's going to be grams of Li2O, 1 mole of Li2O. Now I want to remind you, I want to figure out how many grams of LiOH I can make. So I have to go through moles of everything. So first thing I'm doing, grams of Li2O into moles of Li2O. I want to go into grams of LiOH. But before I go into grams of LiOH, first of all, whatever unit's on top I have to get rid of. Before I go into grams of LiOH, I have to go into moles of LiOH. And then remember, I'm trying to get into grams of LiOH, but before I go into grams of LiOH, I got to get out of this one. Okay, so little g means grams and little g means go to the periodic table. So let's take a look at our periodic table. Oops, hit the wrong one. Our periodic table hopefully will tell us, I think lithium 6.94 it is. So lithium is 6.94 times 2, and then plus 16. 6.94 times 2 plus 16, 29.88. And the number 1 always goes with moles when you're dealing with grams because they have to equal each other. And then here, do you see how it takes 2 moles of LiOH that come from 1 mole of Li2O? Okay. Then I'm back to the 1 and the other one. So 6.94 is lithium plus 16 plus 1.01 is 23.95 equals, so let's do the math, 20 divided by 29.88 times 2 times 23.95, 32.1 grams. So just pointing out again, 3 sig figs in my answer. Now it says how much excess reaction would be left over. I'm going to do a crazy thing. Okay, the crazy thing I'm going to do is I'm going to assume now that this Mayweather reaction with, I'm going to change this number just so we can do it, 20 grams, 20.0 grams of H2O. So that means that I'm going to do pretty much the same thing. But I'm going to start with 20 grams of H2O. And for a limiting reactant problem, I'm still going to convert it into grams of LiOH. 1 mole of water is 18.02 grams of water. Then I got to go into moles of LiOH. 1 mole H2O, 2 moles LiOH, 1 mole LiOH, and 23.95 grams LiOH. So 20 divided by 18.02 times 2 times 23.95 is 53.16. So 53.2 grams LiOH. Now, this is still your right answer, okay, because it is smaller. Okay, remember the amount that's made is always the smaller amount. Okay, so the most I can make with lithium oxide is 32 grams. The most I can make with 20 grams of water is 53. Okay, now the question says how many grams of excess left, how many grams of excess water would I have, basically. So to do that, I'm going to convert this into this and subtract. 20 grams Li2O. 29.88 grams and 1 mole, and then 1 mole Li2O in 1 mole H2O, 1 mole H2O, 18.02 grams. And this will tell me how many grams I need. And I cheated a bit. I didn't Li2O it here. And you should. 20 divided by 29.88 times 1 divided by 1 doesn't do anything, times 18.02. And this number had better be less than 20. And it is. I need 12.1 grams is what I need. It told me I have 20 grams. Oh, nice job highlighting. It told me I had 20 grams. I only need 12.1. 20 minus 12.1, 7.9 grams excess. This is the correct number of significant figures because this was 20.0, and you round to the same number of decimal places. All right, hopping back. Container filled with, before I do that, I'm going to give myself some room on this page. And if I were you, I would just do this on kind of a separate sheet of paper, but I'm not you. I'm just going to Do it this way. Container filled with 0.575 grams of fluorine gas occupies a volume of 125, temperature of 395 Celsius. I hate you, Celsius. I will never let a Celsius thing live long. I'm instantly converting it to Kelvin. 395 plus 273 is 668 kelvins. What is the pressure inside the container? So what I'm dealing with here is a PV equals nRT kind of thing. So the equation I like for this is PV is mass RT over molar mass. What is the pressure? That's what I'm looking for. I've got a volume of 125. No, I don't. 0.125 liters. Try and trick me. Remember, because we use an R that's in liters and atmospheres degrees Celsius, we got to make sure we got the right one in there. My mass is 0.575. My R is on that sheet in case you, I wrote the wrong one. In case you don't believe me, 0.0821. Temperature is 668 in Kelvin. And molar mass, that's fluorine gas. Oh, I'm going to trick you. I'm going to trick you. Fluorine is F2, not F. So I go to the periodic table, and that is 19.00 times 2, which is 38.00. So I'm going to do 0.575 times 0.0821 times 668 divided by 38 divided by 0.125. And I get 6.64 atmospheres, which is wickedly high. So if this was my real class, I'd double check that. That seems like a really high pressure. That's 6.64. But it's not, so. What is the concentration of an aqueous solution containing that many grams in a total volume of this? Molar mass. Hey, isn't that nice? So I know a lot of people do this a different way. I prefer moles equals MV. Okay. So first thing I'm going to do is get moles of this. So 45.5 grams of potassium nitrate times 1 mole potassium nitrate. Didn't think this would come back so hard, did you? 101.11 grams. 45.5 divided by 101.11. Again, 3 sig figs. 0.450 moles. So over here, 0.450 moles equals, what is the concentration? That's what I'm looking for. Milliliters. 0.275 liters. And that's it. M equals my last answer divided by 0.275. And I get 1 point, again, notice everything is 3 sig figs. Okay? 1.64 molar. All right. Student added 216 milliliters of water to 250 milliliters of 4 molar sugar solution. What is the concentration of dilute? I see the word dilute. I'm using my dilution equation. M1V1 equals M2V2. My original dude here is a 4 molar. And I don't have to, but it's a really good practice to just get used to always changing milliliters to liters. You don't have to here. If you want to know why, ask your math teacher, but you don't have to here. I'm looking for the new, what is the concentration? The student added, I did not dilute it to. So 250 plus 216.1 is 466.1. That's my new volume, 0.4661, and then M. Okay, so again, this is 3 sig figs. This one has 4, this one has 4. I'm going to round to the fewest. 4 times 0.25 divided by 0.4661, 2.15 molar. How many picoliters are 980 nanoliters? Ugh. Okay, so I'll be honest with you. Nobody uses picoliters. So let's go to 980 nanoliters. I told you I like to call that E-9 liters. And then since I don't know, I'm going to do what you would have done if no one was looking. How many picoliters are in 1 liter? Guess who I just asked? I asked Siri. Oh, man. Do a quick conversion to give me all these zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It is 12. By the way, don't use your phone on the test. So 1 liter equals 1 E12 picoliters. All right. So on this, I know this is weird. Believe it or not, conversion factors have an infinite number of significant figures because they are definitions. So 980 E negative 9 times 1 E12 is, I wish I didn't have to count zeros again, 1, 2, 3, 4. 98 with 1, 2, 3, 4 zeros. 980,000. Figure out your answer in scientific notation using correct number of sig figs. This has 2 sig figs, and this would be 1, 2, 3, 4, 5. 9.8 E5 picoliters. All right, so let's give myself some more room here. Oh my goodness gracious. Looks like I'm losing some of these things. Write a nuclear equation of following examples of radioactive decay. Okay, well, I'll give myself some room. Beta emission of bromine 82. Okay, let me hit pause. I paused because I wanted a periodic table. My periodic table might differ just by the last digit on the one that was given to you, but I'm still going to roll with it. Beta emission of bromine 82. Bromine 82 is written like this, bromine 82. That dash number is the top number. That is the mass. Okay. I'm looking in the periodic table to make my life a little easier, and it's 35. It does beta emission. A beta particle is 0, negative 1 E. The other particle is 0 plus something equals 82. Something minus 1 equals 35. I go on the periodic table, I look for number 36. That's my old friend krypton. Krypton, but it's more fun to say krypton. Positron emission of K38. 38, 19, K. Positron emission, 0 plus 1 E. 38 equals 0 plus something, 38. 19 equals 1 plus something, that's 18. 18 is argon. Alpha emission of polonium 210. 210, PO. Polonium, I know, is down in the bottom somewhere. I should be able to find it faster. 84. Alpha emission. Alpha particle is 4 over 2 He. 4 plus something is 210. 206. 2 plus something is 84. 82 is lead. Electron capture. Electron capture is the only one that has it on the left-hand side. So if I have Ag106, the silver I think is 47. It is. If it's electron capture, it's the only particle that's on the left. An electron particle, 0, negative 1 E. So 106 plus 0 is 106. 47 minus 1 is 46. Silver then turns to 46 is palladium. Okay, so what you really need to be able to do from here, what you got to do on your own and I can't do for you. You need to know beta emission is this. You need to know positron emission is this. You need to know alpha emission is this. You need to know electron capture is this. And you got to memorize those. So if I walk up to you on the street and said, electron capture, you say, 0, negative 1 E on the left. And that's what you got to do. The Proxima element changed into a different element, like some examples above, is called oof. I don't know what they're looking for here. My guess is transmutation, but it could also be radioactive decay. I don't know which one they're looking for, but one of those is good enough. Identify the type of chemical reaction below, and predict the products. Also indicate if it is redox reaction as well. So redox, remember, the easiest way, one of the easiest ways to do it is so it has an element. If there's an element on one side, it's going to be redox. So this dude right here, identify the type, predict the products. Okay, so I'm going to predict the products. This is combustion, and that is combustion, and it is redox. Okay, and the reason why is oxygen over here has to be 0, and oxygen, remember, is always -2 in a compound. Okay, so we have to do who's oxidized. So oxidation is loss of electrons. So if you lose electrons, you become more positive. It's not oxygen, so it's got to be carbon. Who's reduced? That's oxygen. Oxidizing agent. So the reduced thing is oxygen. Who's oxidized? So I guess who's oxidized would be C2H6. Who is reduced would be O2. The oxidizing agent is the thing that's reduced. That's C2H6 is the agent. That's the reducing agent. And this is going to be the oxidizing. Oops, did I do that wrong? Yeah, I did that wrong. C2. Okay, I'm going to do this a little bit neater. What is oxidized? What is reduced? Ox agent and reducing agent. Okay, oxidation is loss of electrons. If you lose electrons, charge goes up. This went from 0 to -2. That's not what it was. So oxygen is reduced. So my other friend C2H6 has to be oxidized. If you are oxidized, you are the reducing agent, C2H6. The thing that is oxidized becomes the opposite agent. Oxidizing agent is the thing that's reduced. All right, aluminum plus FeCl2. This is going to be a single replacement reaction. So aluminum is going to replace iron, and I'm going to AlCl3 plus Fe. Notice again how I have elements. That's an easy way to tell that it's oxidized or reduced. I'm going to change my color here a little bit. Aluminum here went from 0 to +3. So its charge went up. That means it is oxidized. What's oxidized? Aluminum. So what is reduced? Fe in the FeCl2. The oxidizing agent is the thing that was reduced, right? So Cl2, and then this is going to be Al. CuClO3 is going to decompose. Ooh. I'm trying to remember how this one goes. It is CuClO. Is that it? Hold on. Okay, so a quick little refresher here. I have CuCl plus O2. So chlorates turn into the chloride and O2. Okay, so because chlorate is -1, copper is +1. That's why I get copper 1 here. Okay, look, I have an element. You got to be kidding me. That means it's redox. Let's change our color for this guy to, oh, come on, let me change my color. Oh, let me not change my color. Now welcome to my colorblind world. Oh well. Oxygen went from negative to 0, so its charge went up. If your charge went up, you are oxidized, so that's oxygen. And if your charge changed, so over here, copper's got to be +1, so chlorine's charge must have changed. So chlorine and ClO3 is, so this would be -6, so chlorine would have to be +5. And over here, so chlorine went from +5 and turned into Cl -1. So chlorine had to be reduced. So that's the element that's reduced. Okay. Oxidizing agent, this is weird because it's both of them, because it's the whole thing. CuClO3 and CuClO3. So something that's both oxidized and reduced is rare, but absolutely does happen. It's amphi something I can't think of right now, but that's okay. This one, finally, not a redox one. So if it is a double replacement, it's not going to be redox. I'm going to get KCl plus CaPO4. Now, here's the sad part, you youngins out there. Calcium, remember, is plus 2. Phosphate is minus 3. So phosphate's minus 3, calcium's 2. Potassium's plus 1, chlorine's minus 1. Now, double replacement reactions need to have states of matter. Maybe not here yet, but group 1s are always aqueous, and this is solid. All right, SR plus P, a synthesis reaction. And I'm at SR3P2. Notice I have elements. Oh no! Strontium went from 0 to plus 2. It went up. What's oxidized? Strontium. What's reduced? Phosphorus. And oxidizing agent, remember they're opposites. So the oxidized thing is the reducing agent. And phosphorus is the oxidizing agent. Whoops, I wish I didn't do that. But there you go. All right. Calculate the percent oxygen by mass in K3PO4. So I'm going to do oxygen over K3PO4. So I'm going to do actually 4 oxygens. So 4 times oxygen, 4 times 16 is 64, divided by K3PO4. Potassium is 39.10. Phosphorus is 30.97. And then plus 64 again. So 64 plus 30.97 plus 39.10 is 134.07 times 100. 64 divided by the second answer is 47.7%. Now, they didn't give us any numbers here, so remember we're pulling all these numbers from the periodic table, so they all go to 2 decimal places. So if they all go to 2 decimal places, this is 4 sig figs. So my 47.7 isn't quite good enough. It's 47.74%. All right. Let's see if we can't make this table a little easier. Dot structure. All right, so how I do my dots. Here we go. NH3. I put the central atom on there, and I give it its valence electrons. 1, 2, 3, 4, 5. Remember, valence electrons come from the periodic table. Whatever column you're in tells you how many valence electrons you have. This ends in 8. This is 3, 4, 5, blah, 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 blah. Okay? And then now that I have single electrons, to emphasize that single electrons form bonds, I aim my single electrons at each other, right? And then I sing, connect the dots, la, 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 connect the dots, la, la. That's it, and we're done. ClF2, chlorine is in the 7 column, 1, 2, 3, 4, 5, 6, 7. And fluorine is in the 7 column, fluorine, 1, 2, 3, 4, 5, 6, 7. I don't have a single electron to aim it at. 1, 2, 3, 4, 5, 6, 7. Connect the dots. La, la, la. This is a terrible compound. So really, this should not be ClF2, which doesn't exist very much in nature. Which brings me to what is probably going to be ClF2 negative. But if it shows this, what you do, ClF2, this is the best you can do. The part I really don't like about this is I've got a single electron, which in the way that I do Lewis dot structure, check out my videos, are never allowed, which is why I'm pretty sure that one's messed up a little. This one, okay, so what goes in the middle? The least frequently occurring one goes in the middle. That's sulfur. It has 6 dots. Aiming single electrons, because single electrons form bonds. And oxygen has 6. Connect the dots. La, la, la. Okay, remember I said you don't want to have single electrons? So what I'm going to do here is I'm going to split this apart. You're going to what? Yep. I picked this one up. I'm going to put it over here. And now, but you still have single electrons, but watch what I do here. Pick this dot up and make a bond. So did you see how I moved one up there? and this one up here, and that's how I made that bond. Okay. Now, I know you were taught to count. It feels icky when you do this, but can you tell that oxygen has 2, 4, 6, 8? Sulfur, or this oxygen has 2, 4, 6, 8, and the sulfur has 2, 4, 6, 8, and everybody's happy. So that's good. Molecular shape. So the name of the shape here is trigonal pyramidal. I abbreviated, I know. This one right here would be band. This one here would also be band. Okay. Now, very much a cheating form that works quite well is polar and nonpolar. This works so often. Pairs equal polar. You cannot use that for a reasoning, but it works. Polar. Oh, I got to check the polarity of the bonds. Okay, so let's use that sheet. So my pair and polar thing, but we got to check the polarity of our bonds. So let's see. We got to check what N to H is. So we've got our reference table. I reference you. It's the very last thing on here. The way I got those shapes, by the way, were bonding groups and non-bonding groups. I just matched them up. So I had NH3. N is 3.0 minus 2.1. That's 0.9. That's polar. I had Cl to F. F is 4.0. Chlorine is 3.0. 3 minus 4 is polar. I'm sorry, that's, 1. So remember to be polar. 0.5 and up is polar. And the other one was SO2. Sulfur was 2.5. Oxygen is 3.5. That's 1. That's polar. So there you go. Draw the shape with net dipole, if any. So they all have net dipoles. So here we go. Shape. Trigonal pyramidal. Down. Coming at you. Solid here. Nitrogen is more electronegative. It had the bigger number. So the net dipole is going to be, I want an arrow, from the bottom to the top. With an arrow like that. ClF2 would be Cl. That's going to be bent. F, I guess I'll put a dot here. F. Fluorine was more negative, but the middle of this fluorine is going to be right here. SO2 had 1 pair on the top. Yeah. Double bond. It doesn't matter if you put the double bond on the left or on the right. And oxygen was more electronegative, so it also has that net dipole going down. Intermolecular forces circle all. Everything's got London dispersion forces, you, me, and your mom. This one has hydrogen bonding. Depends on whether your teacher wants you to call it dipole as well. You can if you want to. That's kind of a read your teacher's mind. This one has dipole. This one has dipole. Hydrogen bonding needs to have N, O, or F directly bonded to H. So the tricky one with that is if you have CH, H, H, F is not H bonding. So that's the tricky thing I put on my test. Cl negative and S negative 2 each to 18 electrons, which I always expect to have larger radius. Okay, so anytime I have to talk about periodic trends, which are elements in the periodic table, I talk about size and nuclear attraction. So the size of both of them, they both have 18 electrons. So that means I'm down to my nuclear attraction. So chlorine has, so I'm going to start with this. Chlorine has 17 protons, but sulfur has 16 protons. Sulfur is fewer protons, pull in electrons less, so sulfur's size is bigger than more attractive chlorine. with more protons. All right. Predict the products of the following reaction. Yay. Then draw a particle diagram representing the complete ionic equation for the reaction. Finally, write the net ionic equation. If all species are spectator ions, indicate no reaction takes place. If both equations, be sure to indicate the physical state of each reactant and product. So potassium carbonate is K2CO3. I balance my charges. It wants states aqueous plus calcium sulfide, CaS aqueous, although that's a solid, yields K2S aqueous and plus CaCO3 solid. So this is a group 1. Group 1 is always soluble. Okay, and that's the precipitate. Use your solubility rules. So predict the products of the following reaction, then draw the particle diagram. Representing the complete ionic equation for the reaction. Finally, write the net ionic equation. So when you write the net ionic equation, what you do is you write your product, your precipitate first, CaCO3 solid. And then you just include what makes it. What makes it? Plus 2. I need calcium, and I need carbonate. Now, I don't require people to put aqueous on mine because anything with a charge is aqueous or in the core of the sun. So there you go. So this is my balanced equation, except for I have to balance it. Except it is balanced. And then my particle diagram. So my particle diagram should have, whoa, it's going to draw funny. Should have CaCO3 brick, CaCO3 brick. And then it should have K positive plus S negative 2. So I should have twice as many K positives as S negative 2s. Oh man, I didn't do this right. First, that's what I get for not reading it. So my first one is going to be K positive, K positive, CO3 negative 2. It's got to be neutral when you're done with it. That's why I've got to have that ratio there. Calcium plus 2, sulfur minus 2. Then when I mix them together, I get CaCO3 plus K positive, S negative 2. I'm going to make this in a brick. So that should be sitting on the bottom. Net ionic equation, I drew that up here. I didn't mean to go to yellow anyway. Here's my net ionic equation that you would put right here. A compound called vinyl chloride has this, that, and the other in it. When vinyl chloride polymerizes, okay. Molecular mass of, oh my goodness. What is the molecular formula? So what we're going to do is we're going to do an empirical formula. So we're going to convert our percentages into moles and into whole number ratios. So the first thing I'm going to do is my percentage. I'm just going to assume I have 100 grams. So I'm going to have 38.43 grams of carbon. I'm going to have 4.838 grams of hydrogen. I'm going to have 56.72 grams of chlorine. I'm going to convert that into moles. Go to the periodic table. Go to the periodic table. Go to the periodic table. And get out my calculator. All right, so 38.43 divided by 12.01 is 3.1998. 4.838 divided by 1.01 is 4.79009. And 56.72 divided by 35.45 is 1.6. That's weird. I'll throw some zeros in the end of that. Now, I want to get these into whole numbers. To get them into whole numbers, I'm going to divide by the smallest, which is 1.16. Divided by 1.16. Whoa, that's kind of interesting. Divided by 1.16. 3.1998 divided by 1.16 is 2.75. Ugh. 4.79009 divided by 1.16 is 4.13. This is terrible. And then 1. It's because it's 1.6. Welcome to me not being able to read. Okay, so these should have come out to be either simple fractions or whole numbers, but I can't read my own writing apparently. 1.6 divided by 1.6 is 1. Let's do these again. 3.1998 divided by 1.6. So when people talk about 1.9985, when people talk about number sense, that's number sense right there. So 4.79009. I knew these were supposed to be simple whole number ratios, and this one is 3.00. And they weren't coming out that way. That's why I went, ew, ew, ew. So the formula for this now is going to be C2H3Cl. But the molecular mass is a stinking 23,875. So what I have to do now is figure out how much does this weigh. So I have 2 times 12.01. I have 3 times 1.01. And I have 1 times 35.45. 2 times 12.01 plus quantity. Well, not quite, I still need quantity for that. I can do that in my head. 3.03 plus 35.45. That's 62.5. So I want to know how many 62.5s fit in 23,875. So how many of these, how many 62.5s fit in here? 23,875 divided by second answer, and I get 382. Wow. Okay. So that means I've got to multiply 382 times every subscript here. So 382 times 2 would be C764. H 3 times 382. H1146. And CL382. That's a lot. And this is a lot. That's 48 minutes of fun. So we'll run this one and we'll finish the next one next time. Toodles.